So we'll not calculating the other values. Okay, we'll just focus on only the largest eigenvalue and the lowest eigenvalue of that given matrix. Okay, so before I start, let me just revise the definition of eigenvalue and eigenvector one more time. Okay, so as we know that this eigenvalues and eigenvector, this concept is only for a square matrix. So let A be any n by n square matrix. A non-zero vector x, it's called the eigenvector of matrix A if there exists a scalar lambda such that x is equal to lambda x. So this is the mathematical expression, okay, for the eigenvalues and eigenvector. Means what? If I consider any matrix A of order say n by n, and if I consider the eigenvector x and the corresponding eigenvalue lambda, then how you write this part mathematically? So this can be written as x is equal to lambda x. So this three values satisfies this relation. This is the mathematical relation which satisfies this eigenvalues, eigenvector, and that given matrix. Okay. So using this technique only, we actually develop that power method. Okay, and from which you can directly find the largest eigenvalue or the lowest eigenvalue corresponding to that matrix. Okay, so here this lambda is called as eigenvalue and x is called as the eigenvector. Okay, so I think Sushma also explains some of the applications of this eigenvalues and eigenvectors. Okay, also here I have added a few more applications of these eigenvalues and eigenvectors. Okay, but but not only this, okay, there are actually many applications of these eigenvalues and eigenvectors almost in every domain. Okay, and one of the famous application of this eigenvalues and eigenvector is Google page ranking. Okay, so this algorithm is totally developed using this eigenvalues and eigenvector concept. Okay, so next is it is also used in the communication system, the eigenvalues and eigenvectors, also used in designing the bridges. Okay, designing the car stereo system. Okay, also in electrical engineering. Okay, in mechanical engineering, also the oil companies frequently use this eigenvalue analysis to explore the land for oil. So these are the very few applications I've collected here. Okay, but there are many applications of this eigenvalues and eigenvector. You can directly search on Google, okay, and you can find this application almost in every domain. Okay, okay, so again, that question, why we need this power method? Okay, as I already told you, this power method is a numerical technique from which we'll get the eigenvalue and eigenvector of a given matrix. Okay, so under this topic, what is our aim? Okay, here we have to find the numerically largest eigenvalue or the lowest eigenvalue of a given matrix and its corresponding eigenvector. So with this aim only, we proceed to our lecture. Okay. And what are the drawbacks with our usual process? Okay, so I think you already gone through that lecture. Okay, in previous lecture you have learned how to find the eigenvalues and the eigenvectors of a given matrix using analytical technique. So in that method, basically, okay, first of all we need to consider the characteristic equation of that given matrix. Okay, and after that the roots of the characteristic equation are nothing but the eigenvalues, and corresponding to each eigenvalues, after that we need to calculate the eigenvector. So this is the analytical approach. Okay, but what is the problem with this analytical approach? If I increase the order of this given matrix, for example, let us take one particular example. If I consider a matrix of order 10 by 10, okay, and our aim is what? We have to find the largest eigenvalue or the lowest eigenvalue of that given matrix. See, so to calculate the largest or lowest eigenvalue of this matrix A, okay, we need to calculate, first of all, we need to calculate all these 10 eigenvalues. All these 10 eigenvalues. And to do this, okay, we need to calculate the determinant of this 10 by 10 matrix. So this is the first major difficulty that you face with this usual method. Okay, as we know that for 3 by 3 itself, the calculation of determinant is not that much trivial task. Okay, and and if you increase that order, like say 10 by 10, so so practically it is impossible to find the order of this to find the determinant of this particular matrix. So this is the first difficulty that we are facing with our usual method. And the second difficulty is what? In this method, basically to find the eigenvalues, we need to find the roots of this characteristic equation. And as the order of this given matrix is 10, okay, so to find these all 10 eigenvalues, I need to calculate roots of the characteristic equation, of order 10, of degree 10. Okay, so to find all 10 eigenvalues. Okay, in second case, I need to find the roots of characteristic equation of degree 10. And again, it is a difficult task for all of us, as we know that for degree 2 and degree 3, you can directly calculate the roots from calculator also. But as we increase our order, like say degree 4, degree 5, okay, so so in that case, it becomes difficult to find all those roots of that given polynomial. So for degree 10, it's almost, so practically it is impossible, okay, to find all those roots. So these are the difficulties that we are facing with our usual method. And to overcome this, okay, here we consider this power method. Okay, and one of the strong, the importance of this power method is what? In this power method, you will directly get that largest or lowest eigenvalue. Okay, means what? For example, if I consider a matrix of order 10 by 10, so without calculating those remaining 9 eigenvalues, you will directly find the largest eigenvalue or the lowest eigenvalue, okay, present in that matrix. So that is the benefit of this power method. Okay, in this method, we don't need to find those remaining eigenvalues. अब directly यहाँ पे largest eigenvalue calculate कर सकते हो. Okay, similarly आप directly यहाँ पे lowest eigenvalue calculate कर सकते हो. So that saves our calculation, है ना? So for example, for 10 by 10 matrix, जो 10 eigenvalues का calculation वो डायरेक्टली आपका सेव हो जाएगा, and at then you need to find only one eigenvalue. Okay, so that is the importance of this power method. Okay, so power method. So what we learn in power method, we have to find the largest eigenvalue and the corresponding eigenvector, and the inverse power method is what? The converse of this. So in this method, in inverse power method, we have to find the lowest eigenvalue and its corresponding eigenvector. So this second method is totally dependent on this power method itself. So at the inverse power method also, we have to follow the same steps of power method. Okay, so that also I will explain in detail. So first we'll go with the power method, but before that, let me give some conditions for this power method. Okay, as I told you that you can apply this power method. It's a numerical technique by which you can find the largest eigenvalue and largest eigenvalue or the lowest eigenvalue of a given matrix. But we cannot apply this method randomly for any given matrix. So there are some conditions, there are some restrictions under which only you can apply this power method. So we'll discuss that first. So the first condition is what? That matrix must have n independent eigenvectors. So this is your first condition. Only in this cases you can find the largest eigenvalue and lowest eigenvalue using power method. Otherwise your power method fail. Okay, इन्हीं cases में आप power method से largest and lowest eigenvalue calculate कर सकते हो. So the first condition is what? That matrix must have the n independent eigenvectors. Okay, so for example, if I consider a matrix of order 3 by 3, so as we know that in general, a matrix of order 3 by 3 has less equal n independent eigenvectors. Okay, so in general, if I consider for n by n, so if I consider for n by n, so matrix of order n by n has less equal n independent eigenvectors. But for power method, here we want exactly n independent eigenvectors. Okay, so how you ensure this? Can anyone tell me this? How you ensure this? Can you tell me one case? Can you tell me one case where you will get, where you definitely get the n independent eigenvectors? Can anyone tell me one case where you definitely get that n independent eigenvectors? ऐसा सारे मैट्रिक्स के लिए नहीं होता. For example, if I consider a matrix of order 3 by 3, in this case you may get 2 independent eigenvector, you may get all 3 independent eigenvector, or you may get only 1 independent eigenvector. That count is less equal 3. Number of independent vectors का जो count है, that is actually less equal 3. So it may be 3, it may be 2, it may be 1. But how you ensure that? You must get that n, or like say 3 independent eigenvectors. Anyone? Okay, there is one result related with this. Okay, so every distinct eigenvalue corresponding to distinct eigenvector or independent eigenvector. So if my all eigenvalues are distinct, okay, if my all eigenvalues are distinct, in that case I will definitely get those distinct and independent eigenvectors. So problem आपको कहाँ पे आने वाली है? That problem will come only for a repetition, a matrix with the repetition eigenvalues. Okay, so in that case you have to check whether that matrix has n independent eigenvectors or not. Okay, so for example, if I consider a matrix of order 3 by 3, and if this matrix has eigenvalues say 2, 3, 4, Okay, so since all these three eigenvalues are distinct, so here you will definitely get three independent eigenvector. आपको चेक करने की जरूरत है ही नहीं, यहाँ पे आपको डायरेक्टली यहाँ पे 3 इंडिपेंडेंट आइगनवेक्टर्स मिलने वाले हैं. But if these eigenvalues are in repetition, like say 2, 2, 3, so in that case you may get 2 independent eigenvector or 3 independent eigenvector. So that we need to check. Okay, so that comes under diagonalization. So I think very few are aware about that concept. So यहाँ पे इसलिए मैंने यहाँ पे एक simple result दिया है. You have to just check the eigenvalues. If all these eigenvalues are distinct, then you can directly in that case you will definitely get those n independent eigenvectors. If eigenvalues are in repetition, okay, तो उस केस में आपको particularly calculate करके देखना होगा कि whether you will get that any independent eigenvectors or not. Okay, so this is your first condition. Next condition is what? That eigenvalues can be ordered in magnitude as this: modulus of lambda 1 strictly greater than modulus of lambda 2 greater equal modulus of lambda 3, and so on. Okay, it means what? What is the meaning of this second statement? So that matrix must have only one largest magnitude eigenvalue. Okay, so that matrix must have only one, or unique. Okay, that matrix must have unique largest magnitude eigenvalue. Okay, so for example, if I consider a matrix of order say 3 by 3, okay, and if I take the eigenvalues to be say 4, 4, 2. Okay, so here the largest eigenvalue is 4, which is not unique, means power method is failed in this particular case. But if I consider the eigenvalues to be say 7, 3, and 1, so your largest eigenvalue is 7, okay, and which is unique, means you can apply this power method. Okay, if these two conditions are clear to everyone? Yes, whether these two conditions are clear? Independent eigenvectors, have you ensured that?
Yes, sir.
Have you ensured that that matrix must have that all those eigenvalues must be distinct? Okay, that is the one way to ensure this first condition. Okay, and second is what? That matrix must have unique largest eigenvalue. ठीक है, unique largest eigenvalue, तो ही power method आपकी वहाँ पे work करेगी, otherwise that power method will fail. ठीक है, in other cases that power method will fail. Just tell me, I will ask only one question. If I consider a matrix of order 3 by 3, and if it has eigenvalues like say 7, 2, 2, okay, can we apply power method here? Can we apply power method here?
Yes, sir.
Yes. Okay, yes. Because the largest eigenvalue is unique. 7 is the largest eigenvalue, which is unique. Okay, and the other eigenvalues आपको check करने की वहाँ पे जरूरत ही नहीं है. Okay, no need to check those other eigenvalues. Just focus on your largest eigenvalue. So there are the conditions under which only you can apply this power method. And here, this largest eigenvalue is actually called as dominant eigenvalue. So it has a special name, which is called as the dominant eigenvalue, and the other eigenvalues are actually called as the subdominant eigenvalues of that given matrix. Okay, so these are the conditions to apply this power method. And this power method also has some applications in engineering domain. Okay, here I just collect this one or two applications. The concept of dominant eigenvalue, or the largest eigenvalue, or the lowest eigenvalue of this power method can be used for understanding the solution to practical problems in a broad class of mechanical engineering system described by linear algebraic equation. Okay, it is also used in translational and rotational dynamics, statistics of structures, thermal energy balance, fluid continuity, and feedback control. Okay, these are some applications of this power method also. Okay, and now let us actually discuss the steps to find the largest eigenvalue or the lowest eigenvalue using this power method. Okay, so as I already told you, this is a numerical technique, or this is the iterative process. Okay, so we have to start our iteration with some initial approximation or with some initial eigenvector. है ना, numerical methods में सारे जो iteration आपके आते हैं, with all those iteration you have to start with some initial approximation or with some initial condition. So here in first step, you have to consider an initial eigenvector. Okay, and mostly we prefer those initial eigenvector to be 1, 0, 0. Okay, the first element is 1, other elements are 0, or the all elements to be 1. So in most of the example, we prefer this initial eigenvector. But again, the convergence of this power method is totally dependent on this initial eigenvector. Means what? If I change my initial eigenvector, I may get the convergence in ninth step. Okay, or some other student may get convergence in say sixth step. Okay, so just to ensure this, in most of the example, this initial vector is already given. क्योंकि क्या होता है कि कॉन्वर्जन पार्ट आपका टोटल इनिशियल वेक्टर पे डिपेंड है, तो अगर रैंडमली आप सिलेक्ट करते हो इनिशियल वेक्टर तो आपका कॉन्वर्जेंस, हर एक का कॉन्वर्जेंस अलग अलग होगा. ओके, यू मे गेट दैट कॉन्वर्जेंस इन से 100 स्टेप. ठीक है, तो दैट्स व्हाई इन मोस्ट ऑफ द क्वेश्चन दिस इनिशियल वेक्टर इज ऑलरेडी गिवन टू अस, so that the number of steps that you required for the convergence will be similar for each student. Okay, so again this is a random selection. Okay, in most of the cases we prefer this initial eigenvector. Okay, but you can start with any random eigenvector, and then you have to just ensure that okay, with the minimum number of iteration you will get that largest eigenvalue or largest eigenvector. Okay, so we prefer this, but again you can take any eigenvector, okay, with some condition also that I will tell you later on. Okay, what are the conditions for conditions to select this initial eigenvector also. Okay, but you can take a random vector, random column matrix, and you can start your iteration. Okay, so this is the first step. You have to consider the initial eigenvector. Then next is what? Multiply this given matrix with this initial eigenvector, that is, or just take the product of A matrix with this x naught. You will get some column matrix say x1. Okay, just take the product of given matrix with this initial eigenvector x naught. You will get some matrix say x1. Now from this column matrix it look like this. Just 1 minute. So this x1 is look like this, like say ABC, if I talk about 3 by 3 matrix. Okay, then in next step you have to take the largest or the greatest magnitude value common. Okay, next step हमको करना क्या? From this x, just take the greatest magnitude value common. Okay, with the sign. So suppose that greatest magnitude value is say lambda 1. Okay, so for example, if this value is say -20, 10, and 11. Okay, so can anyone tell me which number we have to take common in this particular case? If my x1, the value of x1 is this, okay, so which number you have to take common? Take the greatest magnitude value. So okay, so which value has the greatest magnitude? Modulus value यहाँ पे large किसकी आ रही है? 20 की आ रही है. Okay, so just take this 20 common, okay, with sign. So just take this 20 common, okay, with sign. So you have to take this -20 common and you have to write in the bracket. So it become 1 and it become -10 upon 20. It become -11 upon 20. This is your first step. Okay, again I will explain one more time. Select initial eigenvector x naught. Let us consider 1 0 0. Then multiply a given matrix with this x naught. You will get some column matrix. Okay, and from that column matrix you have to take the largest or the greatest magnitude value common. Okay, with sign. Okay, with sign, and now we call this as our first iteration or the first iteration of lambda 1 or the eigenvalue lambda 1, and this we called as the x1, corresponding x1. So this is the first iteration for the largest eigenvalue and the corresponding largest eigenvector. In a similar way, now to perform the second iteration. So now for second iteration we have to consider this x1, correct, and multiply a given matrix with this x1. Okay, then suppose this matrix it says x2. Okay, and again from this x2 we have to take the largest or the greatest magnitude value common with sign. So that will be now my lambda 2, and what is whatever is remaining in that column matrix, that we denote by x2. And this gives you the second iteration for largest eigenvalue lambda 2 and the corresponding largest eigenvector x2. So in a similar way we have to perform this iteration. Okay, I will show you here. Okay, now in next step perform. Now this is my the first iteration for largest eigenvector x1. So in next step consider a into x1. Again perform this product, and to perform this product we will use this scientific calculator. तो ये सारी चीजें आप easily कैलसी में कर सकते हो. Okay, so ax1 which is equal to x2. Again take this largest magnitude eigenvalue common, and in bracket you will get some x2. Okay, And so this is the second iteration for largest eigenvalue. This is the second iteration for the largest eigenvector, and continue this process. Okay, and continue this process. So in next step, you have to consider AX3, product of matrix A with this X3. You will get some column matrix X3. Again, from this, take the largest magnitude eigenvalue common, that will be say lambda 3, and what is whatever remaining in that column matrix, that is denoted by X3. Now this becomes your third iteration for largest eigenvalue and the corresponding largest eigenvector, and you continue this process. Okay, so where we have to stop, this iteration. Okay, just check the difference of last two iteration. For example, let us consider here. Okay, so if this is my last iteration, so I have to take the difference of last two iteration, that is X3 minus X2. Just subtract these two column matrix. If this difference is nearly or this difference is negligible or nearly equal to 0, if this difference is negligible or nearly equal to 0, at that time you can stop your iteration. Okay, so you have to continue this iteration. Okay, until and unless if this difference, the difference of last two iteration is negligible. So you have to continue this process until and unless this difference of this last two iteration is negligible. Okay, and then okay, if this difference is negligible, okay, whatever the last iteration is there corresponding to that lambda and corresponding to X, okay, those are your largest eigenvalue and the corresponding largest eigenvector. So that gives you the largest eigenvalue lambda r and the largest eigenvector to be xi. Okay, so process is very simple. You have to just start with the initial eigenvector, then just multiply with the given matrix again and again. Okay, that is our process. So I will explain this whole process with one simple example, and then we'll take some doubts on this method. Okay, so question is like this: determine the largest eigenvalue and the corresponding eigenvector of this matrix. Okay, so here we have to find only largest eigenvalue. Okay, not the remaining eigenvalues. We have to calculate only the largest eigenvalue and its corresponding eigenvector. Okay, using power method. Okay, so just for simplicity, here I will take 1 minute. Yeah, so here I will take a matrix of order 3 by 3, but you can repeat this process of process for any matrix of any order. Okay, so just for understanding purpose, here I consider a matrix of order 3 by 3, and here also I mentioned that initial eigenvector. Okay, so that initial eigenvector is 1 0 0. Okay, and now in solution, let us start our first iteration. Okay, so as my initial vector is x naught, so what is our first iteration? So our first iteration is ax naught. So this is your given matrix A. Multiply this matrix with x naught. Okay, you will get a column matrix which is 1 1 1. Okay, that this calculation you can directly perform on calculator. और ये तो यह इस केस में तो ये सिंपल है, 1 0 0 से अगर आप मल्टीप्लाई करते हो तो in that case you will get a first column always. ठीक है, if I multiply by 0 1 0, you will always get a second column. If I multiply by 0 0 1, you will always get a third column. Okay, or you can directly do this calculation on calculator also. I will explain that part also. So ax naught, that is a product of matrix A with this x naught, so that will be 1 1 0. Now from this we have to take the largest magnitude value common with sign, okay, or the greatest magnitude value common with sign, so that value is 1. If I take 1 common in bracket, you will get again 1 1 0. Okay, now this is my first iteration for largest eigenvalue, so this is my lambda 1 and this is my x1. Okay, now again you have to go for a second iteration. So this is all about the first iteration. Now side by side I will also tell you how you can do this calculation directly on a calculator. Okay, so for that I think everyone having the scientific calculator now. Okay, so I will explain all these steps, how you can perform this whole calculation directly on a calculator. That saves your time. So for that, okay, so first of all we need to open a matrix mode. So mode setup 6. Okay, and then you can directly press AC. So this matrix mode is on now. You can see this mat on your screen. Okay, then just press shift and 4. So all now matrix operation you have to perform under this 4. Okay, here you can see here this matrix word, okay, in yellow color. So just to open this you have to press shift and 4. So now all my matrix operations are under this shift and 4. Okay, now as we have to take here the product of these two matrix, A matrix and X naught matrix. So first of all we need to store these two matrix in this calculator. So to store these two matrix, okay, I will press 2 in data, or in option 2 I will store all these matrices. So press 2. So let me take the first matrix, mat A, okay, of order 3 by 3. So press 1. Let's store this matrix. So 1 is equal to 6 is equal to 1 is equal to 1 is equal to 2 is equal to 0 equal 0 equal 0 equal 3 equal. And after that, just press AC. So that matrix A is stored. Okay. Is this clear? Is this clear to everyone how to store any given matrix? I will repeat one more time. Shift 4, press 2. Okay. यहाँ पे अभी mat A में, here in first option we already stored this matrix A. Now we have to store one more matrix. So now I have to select option B, second. And now this second matrix has order 3 by 1. So I will press 3. Now just store this matrix 1 equal 0 equal 0 equal. Okay. And press AC. Okay. So now here we have stored matrix A, matrix B. Okay. Now we have to take the product of these two matrices. So shift 4. Okay. That store matrix, first store matrix comes under option 3 and second store matrix comes under option 4. So just press 3. So this is your matrix A. Again shift 4, just press 4. So you can see on a screen this mat A into mat B. So this gives me product of these two matrices, and that product is 1 1 0. You can check here. Okay. Okay. And now come to second iteration. Okay. Come to second iteration. Now this is my x1 1 1 0. This is my x1, and I have to keep my A matrix as it is. Okay. And I have to perform now this calculation. Okay. So can you try this on calculator? Can you try this on calculator? This is trivial. Okay. In this case, it becomes trivial. These entries are 1 and 0. Okay. So to perform this, already we have stored our matrix A. Okay. So जो भी changes करने आपको वो second matrix में ही करने. So just change your second matrix. So press AC and now just change your second matrix, which is stored in mat B. Just change your second matrix, which is stored in mat B. Okay. So this is your previous matrix 1 1 0. Now my new matrix is 1 1 and 0. Correct. And now then press AC and again take a product of mat A and mat B. Okay. And that product is 730. Okay. You can 730. You can check here. Okay. 730. And here now we have to take the largest magnitude value common. Okay. Or the greatest magnitude value common. That will be 7. Okay. So this you have to perform on calculator. So 7 in bracket you will get 1. Just divide this by 7. 3 by 7 is this, and 0 by 7 is 0. Okay. Now this become my second iteration. So this is all about your second iteration. Okay. So this is the second approximation. Lambda 2 is the second approximation for largest eigenvalue, and this is the corresponding eigenvector. Okay. But still, if you check this two eigenvalues, आपको हमेशा क्या करना है? Just check the last previous two eigenvectors. Okay. So x1 is 1 1 0, x2 is 1.4860. So there is a large gap between this number and this number. Okay. So we can't stop our iteration here. There is a large gap between these two numbers. So again, you have to go for one more iteration. Okay. So next iteration is ax2. Correct. So this is my x2 now. So matrix A product with this. Okay. Can you please do this calculation? Can you please do this calculation and check whether you get these values or not? Please do it on calculator and give me feedback whether you are actually doing this or not. Yes. So for this again, we need to check only our mat B. So press AC, shift 4. That matrix A is already stored. Okay. Only change the second matrix, which is stored in mat B. Okay. And now this value is 1 equal 0.4286 equal 0. Correct. And now press AC and just take a product of these two matrices. So mat A, that original matrix, and our new matrix is mat 4, that is mat B, and just take this product. This will be 3.5716. Next is 1.8572, and next entry is 0. Okay. And in next step, again we have to take a largest eigenvalue common or largest magnitude value common with sign, but यहाँ पे सारे sign आपके positive ही आ रहे हैं, ठीक है, and in bracket what you get here 1, the next entry is 0.5200, next entry is 0. Again check the difference of last two eigenvectors. So first value is 1, here is also 1, here your value is 0.52, here your value is 0.42, ठीक है. So still that difference is there. Okay, you have to perform the one more iteration, A3. Okay, so if I repeat this same iteration again, you will get this column matrix, and from this you have to take the largest eigenvalue common, which is 4.12. So in bracket you will get 1, and then 0.49510. So this is lambda 4 and x4. Perform one more iteration. Okay, for this particular vector. You will get this, again take 3.9706, the largest eigenvalue common. Okay, now we are here. Okay, and now you check this difference. This is 0.4, this is 0.5. Now this difference is negligible. Okay, if you want, you can stop your iteration here also. Okay, now this, if you're okay, so here I think okay, you can, if you want, you can perform more iteration also. Okay, just to make that difference negligible. Okay, so in next step also you can see this difference. This is now 0.50, this is 0.49. Okay, so here also you can stop your iteration, you can stop here also. Okay, जहाँ पे आपको समझ में आ रहा है कि now this difference is negligible. Okay, at that time you can stop your iteration. So here I consider the one more iteration, iteration number 5. Now just take a difference of these two iteration, this iteration minus this iteration. I will show you that difference also. Okay, so this differentiation, so this difference is nearly equal to 0. Okay, therefore we can stop our method. Okay, at iteration number 6, correct. And also you can see the difference of these eigenvalues, which is also negligible, but at the end you have to focus on only the difference of eigenvectors. Okay, that also ensure the convergence of power method, correct. So at last iteration your lambda 6 is this 4.0072. okay, in last iteration your lambda 6 is 4.0072, which is nearly equal to 4, and the corresponding eigenvector, which is x6, is this 1, then 0.4997, then 0, but this 0.4997 is nearly equal to 0.5. okay, so this is your largest eigenvalue and its corresponding eigenvector. Okay, see the importance of this method here. Without calculating the determinant, without finding the roots of that characteristic equation, okay, here you directly get the largest eigenvalue and its corresponding eigenvector. Okay. Any doubt in this method? I will take one more example. Okay. Now this example is for you all. Okay, please do this calculation on calculator and tell me the values. Okay, so in this example we have to use the power method to find numerically dominant eigenvalue and the eigenvector of a matrix. So a matrix is given, and here I just change that initial eigenvector. So here I consider x naught to be 1, 1, 1. Okay, so yeah, so in solution let us begin with this initial iteration 1, 1, 1. Okay, so your first iteration is a x naught, so a matrix with this 1. Yes, can you tell me this? Okay, if you want, you can directly perform this calculation manually also. Okay, depend on you. Okay, the calculation part is totally depend on you. Okay, manually how you take this product. Okay, first row with first column, that is 15 into 1. I will write this also. Then minus 4 into 1. Then minus 3 into 1. That becomes your first entry. Then second column and this first column, that is minus 10 into 1, plus 12 into 1, minus 6 into 1. Then next is minus 20 into 1, plus 4 into 1, and minus 2 into 1. You can perform like this also. It depends on you. Okay, but in calculator, if I store this matrix A initially, after that I have to just change this second matrix, and that becomes simple. Yes, can anyone tell me what is the value of this?
8, 4, minus 18.
Yes, 8. I think it is minus
8 minus 4 minus 18.
Yes, 8 minus 4 and minus 18.
Minus 18.
Okay. Now, what is my numerically largest value? Which is my largest value here?
Minus 18.
Minus 18. Okay. So just take that minus 18 common with sign. Okay, so you will get this in in the column matrix minus 0.4444, 0.22, and 1. Here I just approximate all these calculation up to digit 4. Okay, you can do this on calculator also. Here I approximate all my calculation up to up to digit 4 only. Okay, yeah, you can directly fix this digit in calculator also. Okay, fix करके भी आप ये सारा calculation कर सकते हो. Okay, now so this is the value of my first iteration. This is my lambda 1 and this is my x1. Correct? So we have to go for our second iteration. So consider A into x1. So A matrix into this x1. Please perform this and tell me the value. Please perform this on calculator and tell me this value. So now you have to just change this second matrix and then just take this product. Just store a matrix A, store a matrix B, and then take a mat A into mat B. Or you can directly do this calculation manually also. 15 into this, minus 4 into this, minus 3 into this. Okay. Yes. Can anyone tell me this value of this column matrix? Please do it. So you have to just practice here in this topic. You have to practice only this calculation. Otherwise, the method is not difficult. Yes. Can anyone tell me this value? Please do it. Tell me at least for this. Yes. Are you doing this or not?
Yes, sir.
Okay. Okay. So I will wait. I will wait. Or you can directly put in calculator also 15 into this, minus 4 into this, minus 3 into this, and you can directly write this first value. So it is up to you which way is convenient for you. Yes.
So minus 10.5548.
Yes, minus 10.5548, correct?
Yes, 1.1104 and 7.7768.
Okay, okay, correct. Okay, and then here the largest minuted value is minus 10.5548 that you have to take common. In bracket you will get this. Okay, again you can check this last two eigenvectors. See this difference. Here it is minus 0.4, here it is 1. The large gap is there. You can't stop this iteration here. Okay, so perform the one more iteration, AX2, repeat the same process. Okay, minus 18.947 to that we need to take common. Okay, and here you will get lambda 3 and x3. Again check this difference. Okay, orally you can check this difference. So it is 1, it is minus 0.9305. Still that difference is large. Okay, you have to go for the next iteration also. Okay, and so AX3, this is your third iteration. AX4, this is your fourth iteration. Okay, AX5, this is your fifth iteration. AX6, this is your sixth iteration. Okay, not only this, AX7. Okay, so here I already calculated all this iteration. A8, 9, and A8, sorry, A8, 9. Huh. So here you can see. So that's why. So this convergence of this power method is depend on your initial eigenvector. So in previous example, hardly within 3-4 iteration you will get that approximation. Okay. Also there is one result. Okay, and in which case you will get the convergence of power method. Okay. So there are some conditions also for the convergence. Okay. So that also I will explain you later on. So here for the initial eigenvector 1 1 1. Okay, in this particular case, at 9th iteration, we will get that convergence. Now you can see the difference here. -1 exactly equal. Correct? It is 0.49. It is 0.49. So very close. 7 6 and 88. So these values are very close. You can stop your iteration here. You can check this difference also. This difference is nearly equal to 0, which is negligible. So the largest eigenvalue is actually lambda 10, and the corresponding eigenvector is x10. So lambda 10 is 19.9904, which is nearly equal to 20, or you can keep this value as it is. Okay, and then the corresponding eigenvector is this -1 0.4988, which is nearly equal to 0.5. Okay, so this is the power method from which you will get the largest eigenvalue and largest eigenvector. But there are some conditions under which only you can apply this power method. Otherwise, what? Otherwise you will not get this convergence. Okay, so जो मैंने initially आपको conditions बोले थे, if that matrix does not satisfy any one of the condition, in that case that power method will not converge to that largest eigenvalue or largest eigenvector. Okay, so under those conditions only you will get this convergence. Okay. So as I already told you, as there are some advantages of this power method, okay, also it has some disadvantages. Okay, so let me give you those disadvantages of this disadvantages with this power method. Okay, so एक statement आपको मैंने initially बोला था, you cannot take a random initial vector. Okay, so this is the condition for that. If your initial vector x0 is the eigenvector of A other that of corresponding dominant eigenvalue. Okay, means what? Statement का पहले मैं आपको explain करता हूँ. If I take a matrix of order say 3 by 3, correct, and suppose it has a 3 eigenvalues. Let us take 3, then 7, then 1. Okay, corresponding to 1, your eigenvector is say 1 1 1. I will randomly assign any vector. Corresponding 7, your eigenvector is say 2 3 4. Okay, and corresponding to 3, your eigenvector is say 0 1 0. Correct. So in this case we cannot start our iteration with this eigenvector and this eigenvector. Why? Because if you perform a power method for this two eigenvector, at the end, like say for this first eigenvector 0 1 0, at the end will converge to eigenvalue 3, and which is not the dominant eigenvalue. Okay, so if I perform a power method for this eigenvector 0 1 0, at the end power method converges to the eigenvalue 3, and which is not the dominant eigenvalue, as for matrix A our dominant eigenvalue is 7. So that is the one disadvantage with this power method. Okay, because we have some restrictions for the eigenvector also, or for this initial vector also. Okay, so just to avoid these two eigenvectors, this is second 1 1 1, and if you perform other than this two, if you take any random vector, definitely you will get the largest eigenvalue and its corresponding eigenvector. So this is your first drawback. Is this clear? Is this clear to everyone? Any doubt in this first statement? Is this clear? What is the problem with the initial vector? Okay. Yes. You can't take the initial vector, which is the eigenvector of the eigenvalues other than dominant eigenvalue. Okay. Like say for 3 and 1, you can't take the eigenvector corresponding to 3 and corresponding to 1 as your initial vector. Okay. Okay. Next is what, as I already told you, this convergences depend on this initial vector also, and also the eigenvalues of that given matrix. Okay, so this is one of the important tool from which you can at least guess the convergence of your power method. Okay, so what is that statement? Just 1 minute. Let me erase this. So the second statement actually gives this condition for the speed of the convergence of this power method. Okay, so if the magnitude of the dominant eigenvalue upon the magnitude of the next dominant eigenvalue, if this ratio is small, this ratio is small, then method converges slowly. It means in that case you need the more number of iteration for the convergence, and if this difference is large, then maybe within 3 or 4 steps you will get the convergence of that power method. Okay, so for example, again if I take a 3 by 3 matrix with some eigenvalues, let us take say 7, 2 and 1. Okay, so here my largest eigenvalue is 7, and upon the next largest eigenvalue is 2. So this difference is what? 3 point something. 3 point something. Correct. So this is the large difference. So here with the minimum number of steps, you will get that convergence. But if I consider here, say 6.5. Okay, so this difference is very small. Okay, and in that case, you will need the more number of iteration for the convergence. Okay, so at the end, you have to ensure this, that the magnitude of the dominant eigenvalue upon the magnitude of the next dominant eigenvalue, this ratio must be large. Okay, then only will get a fast convergence using this power method. If the eigenvalues are very close to your dominant eigenvalue, then it takes that power method takes time for the convergence. Okay, so this is the second drawback, you can say, as in this particular case, that this power method converges slowly. Okay. Now the third case is what? This power method gives only one dominant eigenvalue. Okay. So for example, we cannot apply this method. Yeah, this I already discussed. Okay. We cannot apply this method for eigenvalues like say 4, 4, 1. So this is so here matrix A for the 3 by 3 has the eigenvalues 4, 4, 1. Okay, and we know that its dominant eigenvalue is 4, but we cannot calculate this dominant eigenvalue using this power method, as this value is not unique. Okay, so what is the third drawback with this power method? This power method gives only one dominant eigenvalue. You can apply only for a one dominant eigenvalue, not for more than one. So if that dominant eigenvalue comes in repetition, then this method fails. Okay, so this is the third drawback. And now let us discuss the converse part, that is the inverse power method. Okay, so as we know that this power method gives you the largest eigenvalue on the corresponding eigenvector. So in a similar way, the inverse power method gives you the smallest eigenvalue and its corresponding eigenvector. And we develop this method, or we actually find the numerically smallest and the smallest eigenvalue and its corresponding eigenvector using power method itself. So power method का ही logic आपको use करके here we have to find the smallest eigenvalue and its corresponding eigenvector. Okay, how you do that? So for that, we have to use this result. I think you all are aware about this result. Okay, but still I will explain in detail. So using this result only from power method itself. Remember again, power method means largest eigenvalue. Okay, and inverse power method means the smallest eigenvalue. ठीक है, और आपको करना क्या है, आपको पावर मेथड का ही यूज करके आपको स्मॉलेस्ट आइगन वैल्यू कैलकुलेट करनी है. ठीक है, सो आई एम एक्सप्लेनिंग दैट, एंड फॉर दैट वी नीड टू यूज दिस रिजल्ट. ओके, if lambda is the eigenvalue of a non-singular matrix, what is meant by non-singular matrix? Yes, what is meant by non-singular? Non-singular means
determinant of A is not equal to 0.
Not equal to 0. Okay, so if lambda is the eigenvalue of a non-singular matrix A, if and only 1 by lambda is the eigenvalue of A inverse. Okay, it simply means what? If A matrix has eigenvalue lambda, if A matrix has eigenvalue lambda, that implies A inverse has eigenvalue 1 by lambda. This is the result. Okay, if A matrix has eigenvalue lambda, then A inverse has eigenvalue 1 by lambda. So in a similar way, I can write the contrapositive statement also. If A inverse has eigenvalue lambda, then A has eigenvalue 1 by lambda. These two statements are similar. If A inverse has eigenvalue lambda, then matrix A has eigenvalue 1 by lambda. So using this, can anyone tell me the approach for this inverse power method, or to find the smallest eigenvalue of a given matrix? Can anyone tell me what is my approach? How we actually find that smallest eigenvalue using power method itself, or using the largest eigenvalue itself, concept of largest eigenvalue itself? Yes, if I ask you this question, A is the given matrix and calculate the smallest eigenvalue, provided determinant of A is not equal to 0. Okay, with this condition, with this condition. Okay, I will tell you what is the importance of this condition. Yeah, I will repeat one more time. I have one result. What is that result? I will give you this proof also. If A matrix has eigenvalue lambda, then A inverse has eigenvalue 1 upon lambda. Okay, I can write in a reverse way also. If A inverse has eigenvalue lambda, then A matrix has eigenvalue 1 by lambda. So this is one result with us. Using this, can anyone tell me how we find the smallest eigenvalue of matrix A using power method itself? How you find the smallest eigenvalue of matrix A? Yes, this is open question for all. Hint already मैंने यहाँ पे consider मतलब I already given you the hint. Anyone, can you try how you find the smallest eigenvalue using power method itself? Somewhere we need to use this part. Anyone? Anyone? How you find the smallest eigenvalue of A? As we know this result that A inverse has eigenvalue lambda, then A matrix has eigenvalue 1 by lambda, or A matrix has eigenvalue lambda, then A inverse has eigenvalue 1 by lambda. How you adjust this concept to calculate the smallest eigenvalue of a given matrix A? Can anyone tell me this? Okay.
So
As this, yes, ma'am.
AX0 is equals to 1 by lambda x1. Will it be possible? So I just guess, sir.
No. Okay. As this determinant of A is not equal to 0. Okay. As this determinant of A is not equal to 0. Okay. Can I find A inverse here? Can I find A inverse here?
Yes, sir.
Okay. This is the condition for existence of inverse. Okay. Inverse exists only when your determinant is not equal to 0. So as I already told you that in every example on inverse power method, determinant of that matrix must be non-zero. Okay. So I can find that A inverse. Okay. Now instead of matrix A, I will consider A inverse. Okay. Here we have given matrix A. Okay. After that, calculate its inverse. Now instead of this matrix A, now do that all calculation for A inverse. And using power method, calculate largest eigenvalue of A inverse and follow the same steps for A inverse. Okay, जो आपने अभी previous method में learn किया था. Use those similar steps and calculate the largest eigenvalue of this A inverse. Suppose that largest eigenvalue is lambda. Suppose that largest eigenvalue of A inverse is lambda. Can you write the smallest eigenvalue of A from this? If the A inverse has the largest eigenvalue is say lambda, then what is the smallest eigenvalue of A?
1 upon lambda.
1 upon lambda. Okay, 1 upon lambda. So directly you can write the smallest eigenvalue of A, which is 1 by lambda. And here we use this result. Okay. तो इसमें लॉजिक क्या है, आपको A मैट्रिक्स के स्मॉलेस्ट आइगन वैल्यू कैलकुलेट करनी है. तो आप क्या करो, आप A इनवर्स के लार्जेस्ट कैलकुलेट कर रहे हो, फिर उसको रिवर्स करके आपको ऑटोमेटिकली स्मॉलेस्ट आइगन वैल्यू मिल रही है. दिस इज द लॉजिक बिहाइंड दिस इनवर्स पावर मेथड. Okay, do that whole calculation for A inverse. Okay, and calculate the largest eigen value of A inverse. Now just reverse that 1 upon that lambda, that become the lowest eigen value or the smallest eigen value of matrix A. Okay, and to calculate this A inverse, we need that determinant to be non-zero. Okay, so therefore for this inverse method, we have these conditions. This proof is there. I'm not going detail now. Yeah. So now these are the so here in this case I need to add one more condition for this inverse power method. Okay, अगर आप power method की condition check करते हो ना, power method में in that power method we have only two conditions, this and this. First condition क्या थी? That matrix must have the independent independent eigenvectors, and second that matrix must have only one dominant eigenvalue or only one largest eigenvalue. These are the conditions for power method. But for inverse power method, we need this A inverse. Okay, so we have to add one more condition. That condition is what? That matrix A must be a non-singular, or simply I can say that determinant of this matrix must be not equal to 0. So we have to add this one more condition for this inverse power method. Okay, is this clear? Approach of inverse power method is clear to everyone? If you have any doubt, you can ask me directly. I will explain one more time. Okay, is this approach clear to everyone?
Clear, sir.
Okay. Now we'll take one example on this method. Yeah. So this is the last part. from my session. So find the numerically largest eigenvalue and its corresponding eigenvector of A inverse using power method. एक तो आपको इस फॉर्म में क्वेश्चन आ सकता है. Okay, so I think I already explained all these steps, है ना? So these are the steps. Just calculate the largest eigenvalue for A inverse and just reverse that. Lambda dash आपको reverse करना है 1 upon lambda dash, that become the smallest eigenvalue of matrix A. As I already explained all these steps, you can refer this PPT also. Okay, now let us discuss this method directly from one example. Okay. So use inverse power method to approximate the least eigenvalue and the corresponding eigenvector of a following matrix. This is our question. So we have given that matrix. Also we have given the initial eigenvector. Okay, आपको मैंने पहले clear किया था कि almost in every example this initial vector is given. If not given, then you can try 1 0 0 or 1 0 1 1 1. Okay, you have to go with the random selection. There is no logic for this. You can go with the random selection. Okay. But in most of the example, that initial eigenvector is given so that you can calculate calculate the convergence of that power method. Okay, या सब सारे student का convergence equal आना चाहिए उस केस में. Okay, so now in solution, as we have to find the smallest eigenvalue of this matrix A. Okay, so instead of this, first we consider its inverse. Okay, just consider the A inverse. I will explain one more time how you can find this A inverse on calculator. I think most of the players are aware about this. Yeah, so how you calculate this A inverse directly on a calculator. So for that, again, we need to store that matrix A in a calculator. Okay, so shift and 4, store that matrix in a calculator. Now I will take a third matrix C of order 3 by 3. Just put all these entries: 1 equal 2 equal 3 equal 0 equal 1 equal 4 equal 5 equal 6 equal 0 equal. Then press AC and then again shift 4. Okay, I have to find inverse of mat C. So that mat C is stored in 5. Now I have to find its inverse. So for inverse, there is a special button on this calculator which is X inverse. Just press X inverse. So mat C inverse, that gives you the inverse of this matrix, which is minus 24, 18, 5, 20, minus 15, minus 4, minus 5, 4, and 1. Okay, that saves your time. Okay, so just calculate this inverse directly from scientific calculator, and then now use the power method. Now use the power method for this A inverse. After that, all the steps are similar to power method. So as I already told you, this is just the repetition of power method itself. Okay. Okay, now so this is our initial vector. Take the product of this A inverse. Okay, now this is my A inverse. As a typing mistake. So A inverse with this X naught, or the given matrix with the X naught. Okay, so now you can do this product. Okay, so that product is minus 1 1. Sorry, minus 1 1 0. Okay, now so now here you are. See, so in this case, your largest value is 1. Correct, your largest value is 1, and now there is a problem with sign. Okay, that minus sign is also there, that 1 sign is also there. So in this case, you can take minus 1 also common, or you can take 1 also common. Okay, as we know that we have to take that largest eigenvalue common with sign. Okay, but at first entry that sign is minus, at second entry that sign is plus. Okay, so you can take plus sign, you can take minus sign, that will not affect your answer. Okay, so here I take that positive sign for that largest eigenvalue, just to avoid those minus sign. Okay, so if I take that 1 common, you will get minus 1 1 0. Correct. Now that become my first iteration and corresponding the first eigenvector. Correct. Now again A inverse into x1. Okay, so this A inverse multiplied by this X inverse minus 1 1 0. Do this calculation. You can perform this calculation on calculator. You will get this. Now the largest eigenvalue is 42. Okay, so just take that number outside. In bracket you will get 1 minus 0.8333, 0.2142. Okay, and this is my lambda 2 and x2. Here you can check this difference is large now, minus 1 1 1 and this. So you can't stop this method here. Perform one more iteration. Okay, so in every case there is a inverse. Okay, you will get this. Take the largest eigen value with sign outside to this column matrix and repeat this. Okay, So repeat this. So at this third iteration, you will get the eigenvector to be this 1 minus 0.8343, 0.2141, and here you will get 1 minus 0.8343, 0.2141, exactly equal. Okay, exactly equal. Therefore, you can stop this iteration process here. So this x4 minus x4. Okay, if I check this difference is exactly 0, and also your eigen difference between these eigenvalues is also negligible. Okay, so you can stop this iteration at this third place. Okay, and at third place your lambda 3 is this and your x3 is this. Okay, now sorry, this is 4. This is 4. So at third iteration your lambda 4 is this and your x4 is this. So the numerically largest eigenvalue of A inverse is actually lambda 4 equal to this, and the corresponding eigenvector is this. Okay, now so using this, how you write the numerically smallest eigenvalue of matrix A. Okay, how you write the numerically smallest or the lowest eigenvalue of matrix A. So that will be just reverse of this 1 upon lambda 4. That gives you the smallest eigenvalue. Of matrix A. A inverse की अगर lambda 4 आपकी eigenvalue है, तो A matrix की eigenvalue क्या आएगी 1 upon lambda. ठीक है? But in that case, in both cases, for A inverse and for A, in both cases your eigenvector will remain same. Okay, so here इस केस में आपको x4 के एंट्रीज को आपको रिवर्स नहीं करना है. ठीक है, so that x4 will remain same. Your eigenvector will remain same for A matrix also, for A inverse also. Okay, I will tell you that proof also why this vector will remain same. Okay, and this is your final answer. So there is no change in the eigenvector that you can write for A inverse also, that you can write for A also. Okay, only change you can find in eigenvalues. Okay, so for eigenvalues you need to take this inverse 1 upon that lambda 4. Okay, so this is the smallest eigenvalue and its corresponding eigenvector. Okay, so why this happen? Why this eigenvector is not changing here? So here I will give you one quick proof of this and then we'll stop. Okay, so why this happen? Why this eigenvector will remain same in both cases? Okay, so what is given? We have given a matrix A. We have given eigenvector x, we have given eigenvalue lambda, correct? And also the determinant of A is not equal to 0. These all things are given. Okay, so as we know that if we have a matrix A with eigenvector x with eigenvalue lambda, so there is a mathematical relation between these three values, that is x is equal to lambda x, correct? Or this is the definition of eigenvalues and eigenvector. But as my determinant of A is not equal to 0, okay, that implies your A inverse is exist. That implies your inverses exist. So you can multiply this equation by, okay, so this mathematical expression tells you that this matrix A, okay, what is the meaning of this mathematical expression? This matrix A has eigenvalue lambda and corresponding eigenvector is x. Okay, now as my determinant of matrix is non-zero, that implies A inverses exist. So just multiply this equation by A inverse. So that gives me A inverse into A into x is equal to A inverse into lambda x. A inverse into lambda x. Okay, now A inverse into A. Okay, this gives you identity matrix. So x is equal to A inverse into lambda into x. That implies I can shift this lambda on LHS. So you will get I will write first this LHS. A inverse x is equal to, now here I shifted this lambda on LHS, that you can write it as 1 by lambda into x, and you can compare this equation with this. As I already told you, this mathematical expression tells you that this matrix A has eigenvalue lambda and eigenvector is x. So this mathematical expression, this we calculated in second case, this mathematical expression tells you that this A inverse has eigenvalue 1 by lambda and eigenvector is x. So you can check from this also. A matrix has eigenvalue lambda, eigenvector x. A inverse has eigenvalue 1 by lambda, but eigenvector will remain same. That's why you are not supposed to change the eigenvector that you calculated from the power method. You have to just change the eigenvalue, means replace lambda by 1 by lambda. Okay, is this clear? Is this clear why we have to keep this eigenvector same? Yes. Is this part clear to everyone? why I'm keeping this x4 same for A also and for A inverse also, because of this statement. A inverse x equal to 1 by lambda x. So for A inverse, your eigenvalue is 1 by lambda, but your eigenvector will remain same. Okay. So I think this is all from my side. Yes. Yes, any questions, any doubts regarding this topic, power method and inverse power method? So in this method, basically you have to find the largest eigenvalue or its corresponding, or the lowest eigenvalue of a given matrix. Okay. And this is the numerical techniques, iterative process. Yes, any doubt? Any doubt in any particular question or in any method? Just tell me. Okay, so I think if you don't have any doubt, then I will stop here. Okay. Please fill the attendance and feedback link for session 2. And we'll meet at 3 for second session. So third session, last session. Okay, then we all will meet at 3:30 for our third session, data analysis methods and tools by Dr. A. Thakre. That will be our last session. Thank you all.
Thank you, sir.
Yes, thank you, sir. Okay, sir. Sorry, I was just went for something.
Yes,
Thank you,
ma'am.
sir. Thank you for a wonderful session. Okay, participants. So we can meet now at 3:30. Kote sir, I'm not able to just stop recording. So can you please from your side?
Yeah. Yes, ma'am. Just let me check.
Because electricity was gone, so maybe host koi aur ho gaya hai, so I'm not able to stop that recording.
Okay, ma'am. Just let me check.
Renu ma'am, can you check, because after me you join, so maybe host is now you.
नहीं मैम, मेरे यहाँ से भी शायद नहीं हो रहा है. मुझे भी कॉल आया था, तो बिकॉज ऑफ दैट इट इज